All right. It's Alessandro, right?
It is.
Alessandro is going to talk about particle models.
All right. Hi, everybody. My name is Alessandro. I'm from the University of Pittsburgh. Before I start, let me say it's a great pleasure and honor to host JuLDPM here at Pitt this year. So I hope you're enjoying the conference so far. So today I want to talk about some of the work that me and my research team have been developing for about a decade now about different types of approaches that are really brought together by this idea of lattice modeling for quasi-brittle fracture. The package should be out relatively soon. It has this very uninspired name of JuLDPM. I will tell you a little bit in a second. But so in general, we're very interested in understanding how materials degrade and fail over time. Particularly, I'm very interested in quasi-brittle, brittle, and quasi-brittle material. And so the vast majority of the work that we do has to do with cementitious composites, so plain and reinforced concrete structures, fiber reinforced polymers, as you see here. These are some GFRP elements that are commonly used in structural applications. And then, of course, geomaterials, and we've done a lot of work with soils and flood protection in particular. So we're very interested in understanding how different scales contribute to degradation and failure, and particularly in being able to simulate and model numerically such effects over time. And the vast majority of what we do, the package is really implements this lattice discrete particle model approach, which was originally developed by Dr. Gianluca Cosaris at Northwestern University. And so in brief, I'll give you a little flavor. Because of time constraint, I will just give you a brief flavor of what this looks like, but in general, given a three-dimensional domain, the idea is that we can saturate a three-dimensional domain with poly-sized spheres. For the specific application to concrete, then these spheres also represent the granulometric fraction of the coarse aggregate particles themselves, so that we have a so-called mesoscale representation of the material. Then if you take all these centroids of all these particles and you perform a Delaunay triangulation, then you obtain a very dense network of 1D elements. So all the edges of the tetrahedra that are obtained from the Delaunay provide you with this very dense network of elements. We call these the lattice elements. And so the general idea is that we schematize the three-dimensional behavior of the material, of the continuum, as a discrete interactions on these 1D elements. This brings a lot of interesting sort of advantages, particularly because all of your tensorial constitutive relation become vectorial at the 1D level of the lattice struts or elements, as we call them. So what this looks like, if you could zoom in detail into one of these lattice elements, then you have this line that connects two of the spheres. We build this centroidal tessellation around each sphere, which provides with the discrete particles that we assume rigid, on which we schematize the material behavior. Now, what this looks like more in practice is this. So each of these rigid particles is effectively the volume of influence of each of the spheres. And so this is what the idealization of the material will effectively look like at the mesoscopic scale. The idea is that, especially for concrete, this is really a direct representation of the fracture itself, because the fracture is governed by mostly the tortuosity that's induced by the fact that the particles have different sizes and orientations, and so you have this direct representation of that, of these fine-scale features that provides a lot of advantages when simulating fracture. I'll give you just a couple of examples now. As I said before, we use vectorial constitutive models, which means that the model generation is relatively more tame than when you have to describe fracture in a tensorial framework, because now you can enforce exact fracture energy release rates for mixed mode fracture, which means when you have mode 1, which is tension, and mode 2, which is shear fracture, then things become really complicated in a 3D sense, but in a 1D, at the 1D level of each of the lattice elements, you can really enforce very complex fracture models. So you see some of them here for tensile behavior, shear interaction with tensile behavior, where the different levels of compression basically provide more frictional resistance to shear fracture at the lattice element level, and so on and so forth. If you're more interested into the details, which I'm going to have to skip, you can please refer to some of these recent papers that my group published. But in practice, I want to give you more of a flavor of what the simulations look like. Effectively, you have this very dense pack of particles. These are uniaxial compression tests, very common, very, very standard so for anybody who is a structural engineer or a civil engineer. And so what you see here is that effectively not only we were able to capture, you can very accurately capture the stress-strain response. These are completely blind predictions that you see here, but not only the stress-strain response, which of course is achievable by many types of models, but what is generally not as easily achievable when you're representing fracture is also the capturing of the fracture patterns, which is again at this scale, which is the mesoscale level of the coarse aggregate particles, is a very accurate representation of very complex fracture patterns, as you see here when comparing the experimental and the numerical results. Okay, so this is sort of a long preamble, but this is the capability of the model. I want to show you some of the things that we recently implemented and added to the model, where in the development of all this, of the JuLDPM package. Here you see some very nice representation of a simulated failure. We call this the hourglass failure, which is very well sort of predicted by the model. Now, we recently started working into extending this method to introducing rebar. Of course, when we talk about reinforced concrete, rebar is a very critical component. And so in order to do this, we devised this technique, which is slightly different from what is traditionally done. And we do this as follows. So we first place the nodes that pertain to rebar in the domain, as you see here, which effectively mimics how you cast the models, because you first lay rebar and then you pour your concrete. And then we still fill the space with this polycide sphere, exact same, but then now you have to use a constraint Delaunay tetradiarization to make sure that your rebar nodes are still connected by the Delaunay, as you see here. And so you get this, again, very dense network of 1D elements, and then we restructure the entire method to understand what are the interactions with between the parts. Still, we perform the standard LDPM tessellation, but now this is a little bit more interesting because it's a little bit more complicated. And so what happens is that now we have the coexistence of 3 different types of lattice elements. So if you look around each of the rebar elements, you have particle nodes, which represent the concrete, that interact with your rebar nodes, obviously. And so you have 3 types of nodes. So you have the concrete element, which is concrete to concrete node. Then you have some form of contact element or bond slip element, sometimes it's called in numerical modeling. So you have, whenever a concrete node is connected to the rebar, so such as one of these 2 inclined members, that's of course a contact lattice element, and then you have all the steel elements, which are of course rebar to rebar. Once you do this, then you have obviously to apply 3 different constitutive behaviors, because the constitutive behavior, the response to mechanical deformation of these 3 different types is extremely different, and so you have to account for that. And in this case, I want to show you just the only snippet I'm going to be showing you about all the code is that one part I really like about particularly using Julia, but in general, I think some of this implementation is very elegant, is that we have separate structs, obviously, for the different types of elements, but then you can use multiple dispatch in your constitutive function so that you can effectively dispatch the correct function depending on the types of elements. Then just a couple of very, very quick results. So you can simulate, we are able to simulate and replicate very complex fracture pattern. This is a 4-point bending test under symmetric reinforcement conditions and non-symmetric forcing conditions. So you see here that this is a DIC, which is a digit image correlation that provides you with a strain map in 2D, and you see that, of course, we can represent such very complex fracture patterns particularly accurately. And here I have some sort of computational efficiency analysis granted by a lot of fantastic work. Particularly, the package uses linear solid sparse pack, JuliaDiff, some of the JuliaSim, and some of the automatic differentiation tools that are available in Julia, which was fantastic help in the development of this. And with this, I thank you.
Thank you very much, Alessandro. So unfortunately, we don't have time for questions. It's 10 minutes. So it feels like next year you need 30. So we can try to figure that out. But yeah, thank you very much.
Thank you.
And we're on to the next